Hey guys, today we're going to be looking at molecule shapes for covalent compounds. Covalent compounds share electrons to form bonds between their atoms and fulfill the octet rule. And the way that these electrons are shared determines the shape of the molecule. And we call that the VSEPR theory, which stands for valence shell electron pair repulsion. We can see the placement for all of these electrons in things called Lewis dot structures, which are kind of similar to Lewis dot diagrams. Here's a picture of one for carbon bonded with 4 hydrogens. It shows each hydrogen atom and a bond between the hydrogen and carbon. And what you can't see is that these bonds are actually just 2 electrons that are shared in that space between the atoms. So each bond is made up of 2 electrons. That's where the electrons are like living inside of the molecule. The places where the electrons are living inside the molecule are called areas of electron density around the center atom. So bonds count as areas of electron density, but sometimes you could also have some electrons that are not in a bond, that are by themselves. Those we'll call a lone pair. They'd look something like that. Just 2 electrons chilling on the center atom there. Now, the number of bonds and the number of lone pairs in the molecule is going to determine the shape of that molecule. And we've got a chart here, which you do not have to memorize. You'll be given. This chart tells you how to find the shape for each of the molecules. So let's look at this carbon with 4 hydrogens right there. And we're going to see, as an example, what shape it is. So the way we do that is we count up the number of bonds that there are and the number of lone pairs on the central atom. So I'm going to count all of the bonds with my yellow highlighter. Got 1 bond, 2 bond, 3 bonds, 4 bonds. Write that down, 4 bonds. And there's no electrons randomly chilling, so there are 0 lone pairs. And we can just go find that on the chart. Starting with number of bonded areas, that is 4, which we find right there. And there's 0 lone pairs right there. So this shape, which is in this column right here, is a tetrahedral molecule. And that is about as simple as it gets. You just count the number of bonds, count the number of lone pairs on the central atom, and you find it on the chart. Look at the shape. Let's go look at some examples. So we're going to look at each of these molecules that is here on the left side of the screen, and we're going to figure out exactly what shape these things are. And we do that by counting number of bonds and number of lone pairs. So number of bonds on this first one is 1, 2, 3 bonds. So over here under number of bonded areas, I'm going to put 3. And the number of lone pairs is the number of random pairs just chilling on the center atom only. So we've got 1 right there. That is a lone pair. And I know that's 2 electrons, but 2 electrons makes 1 pair. So we put 1 number of lone pairs right there. We're going to go find on our chart over here that I've conveniently pasted for you something with 3 bonds. So there's 1 and there's 1. And 1 lone pair right here. Number of bonds, number of lone pairs. That makes this one trigonal pyramidal. So over here for molecular structure, I'm going to write trigonal pyramidal. And I'm going to write it sideways so it'll fit. But really, all I did was go take the number of bonds, number of lone pairs, find them on this chart or this table, and drop them over here in this table. And we're going to fill in the rest of the things accordingly. The number of areas of electron density is equal to bonds plus lone pairs. So 3 plus 1 equals 4. The bond angles come from this chart. For trigonal pyramidal, it's approximately 107 degrees. And the molecular polarity is polar. Something you're going to have to know, and you're going to have to memorize because it won't be given to you, will be polarity. Polarity is basically whether the molecule is entirely symmetrical or not. And the way you can tell is if it's got lone pairs. If it has lone pairs, it is polar. If it doesn't have lone pairs, so no pairs, it is non-polar. So P for pairs is P for polar. NP for no pairs is NP for non-polar. Well, let's go look at this second molecule here. We start off counting the number of bonds. Now this one can get a little tricky because those are some double bonds, but they still only count as one bonded area each. So that right there is 2 bonded areas. And the number of lone pairs is only ones on the center atom. So these ones on the outside, they do not count. There are no lone pairs on that center atom. So we put 0. And go look on the chart for something that's got 2 bonds. So we've got that one or that one or that one with 0 lone pairs. So 2 bonds, 0 lone pairs. That is linear. Go over here, right? Linear. Add up those two numbers to get the total areas of electron density. 2 plus 0 is 2. If you forget how to do that, it's also on your handy dandy chart. The bond angle is on the chart. It's 180 degrees. And this one doesn't have any pairs. No pairs is non-polar. I'm just going to write NP for non-polar. And last example down here is H2O, which is water. First thing we do, count up the number of bonds. We've got 1 bond, 2 bonds, and then we count the number of lone pairs. 1 pair, 2 pairs, 2 lone pairs. So we're going to go on the chart over here. See, I'm going to erase the chart real quick so that we can look at it clean and clear once again. Okay, we're looking for 2 bonds and 2 lone pairs. 2 bonds, there's 2, there's 2, there's 2. 2 lone pairs is right here. So this one, water, is bent because it's got 2 bonds, 2 lone pairs. Add those up, you get 4 areas of electron density. Bond angle comes from the chart. It's approximately 104 degrees. And this one does have lone pairs, so it is polar.